Good afternoon, everyone. My name is Mohit, and on behalf of Aalto University, I welcome all of you to the second HAIC Talk of this year. And since there is many new people who are joining us virtually on this call, I will take a couple of minutes to briefly introduce HAIC. So HAIC stands for Helsinki-Aalto Institute for Cybersecurity. It was started in 2016 as a joint initiative between University of Helsinki and Aalto University with three main goals. The first, to foster joint research between the two universities as well as the security industry in the capital area. The second, as some of you may know, that Finland now has tuition fee for international students coming from outside the EU. And both the universities were concerned that this would affect the number of students specializing in information and cybersecurity. So we reached out to our industrial partners for donations to provide scholarships to students. And I'm happy to announce that in addition to our usual donors, F-Secure and Huawei, we have a new donor, SSH, Communication Security. So many of you will be familiar with SSH, the protocol, but SSH Communication Security is also a listed company headquartered in Finland. I would also take this opportunity to ask if any of you are working for a security company in Finland and want to provide donations to us, do reach out to us. Any money that you give is used directly for providing scholarships to students. Similarly, if you're a student who is thinking about specializing in security, do reach out to us. We have scholarships available. The third and final purpose of HAIC, which is why all of you are here today, is that we have a public outreach program. So we invite experts in the field of cybersecurity to give enlightening talks. And we also provide you with an opportunity to interact with them and ask them questions. So there will be a half-an-hour Q&A session at the end of today's talk, and you will have the opportunity to ask questions. We will enable chat and also allow you to unmute yourself and ask questions directly to our speaker. This outreach program is possible thanks to the generous funding by the Dean of School of Science at Aalto University. So today's talk is going to be about IoT security. This is obviously a topic close to my heart. I did my PhD research in the area of IoT security. And without further delay, I would like to introduce our speaker for today, Hannes Tschofenig. So Hannes is currently a distinguished engineer at ARM, and in the past he has worked for Siemens, Nokia Siemens, and the European Data Protection Supervisor. Over the last 15 years, he has been active in the IETF, where he has been working on standardizing protocols for making the internet more secure. He has authored almost 90 RFCs, and he has been chair of several working groups at the IETF, such as OAuth, ACE, DIME, and many others. In the past, he was also a member of the Internet Architecture Board, and currently he's the board member and chair for Device Management and Service Enablement Working Group of OMA SpecWorks. And since I know Hannes personally for past several years, I would add some anecdotes. So I have been participating in the IETF with Hannes, and he knows a lot about a lot of different things. So no matter whether I work on TLS or DTLS or OAuth, he knows them inside out in a lot of detail. And not many of you may know this, but Hannes is also a long distance runner. So when I say long distance, that's not just half marathons or marathons. He's doing ultra marathons of 100 kilometers or more. So with that, Hannes, the floor is yours. I'll stop sharing and hand over the controls to you.
Thank you, Mohit, for the nice work, and thank you, Nina, for inviting me. Seen a couple of well-known names in the participant list, so I'm looking forward to some tough questions in the end. Okay, I hope you can see my screen by now.
Yes, we see it. Well,
okay, cool.
Yeah.
So as mentioned, like I've spent a lot of time on security, and security is such a broad field. So whenever I go to some hacker conferences like Black Hat and DEF CON and so on, I'm always wondering about the huge difference between the number of people who work on trying to make the internet more secure and the number of people who are interested in breaking it. It's just totally disproportionate. So I'm happy to have so many participants here who actually are interested to improve things rather than just hack them and break everything. What would be a talk about standards without actually diving straight into some of those? Mohit, you may have been involved in some of that work. And talking about IoT, if you look at the IETF specifications, then I mean by this terminology for so-called constrained node networks, or IoT, has been taken over by other organizations. I've seen those terms and used by NIST specifications and by other industry associations. And so what it ultimately sort of points to is that with IoT, there are some constraints. There are constraints in terms of flash, and the constraints in terms of RAM, processing power, user interface, and so on. So, and then many of you who have worked on real hardware will be familiar with those constraints. Cortex M-class devices will probably be very familiar to you because those have those constraints. They are very also low cost, as you can imagine, and that's important for the billions of devices that we already have in the market. Likewise, the networks are equally constrained. So over the last 10 years, we've seen a number of radio technologies who have very low data rate, they have high latency, they have a lot of loss rates or high loss rates and other constraints. If you think about LoRaWAN, maybe even some of the later cellular networks who are not as performant as some of the networks we are using for everyday communication, like on your laptop, on the laptops and desktops and so on. Sorry, my cat drives me nuts. For those who have a cat at home, you may know that they always show up and make some noise. There are these, or the document, this RFC then, besides providing these sort of distinction of what IoT actually is, it also goes into the different classes of devices and talks about 3 classes. Class 0, which is essentially unfit for the internet. Class 1, which is can be connected to the internet, but requires some special purpose protocols to actually do so, because the RAM size with around 10 kilobytes and the flash size with 100 kilobytes is obviously very, very aggressive, or an aggressive constraint. And then class 2 is something that is sort of a more in the manageable part for most purposes, where you can use general purpose internet protocols. However, if we look at devices that people actually produce, and I picked 2 examples here of wearables, and obviously they serve the same purpose, smartwatches that communicate over Bluetooth, and they actually are under the hood. If you look at the hardware and the software, they are very different. They couldn't be different. One is Cortex M4, and the sort of M-class device, quite constrained, probably very similar to what I mentioned on the previous slide in terms of RAM and flash and processing power and so on. But then on the left-hand side, you see sort of an A-class design, which is something that is, I would say, very powerful, very capable processor, having sort of all capabilities of a modern computing device, a general purpose computing device. So obviously it runs Linux, Android, and it's very powerful. So we obviously don't know the decision-making process in this for those products, but it's something that many developers face when they are working in companies trying to do their best to develop secure IoT devices. They're obviously driven by different incentives. They have a certain use case in mind, a different business model. And so they need to make technology decisions, which have significant impact on sort of the rest of the product lifetime, and also their development efforts. And to make this a little bit simpler, my colleagues have come up and spent many years on what is known as the platform security architecture, or PSA, to develop sort of a scheme, I would say, with 3 pillars, which starts off with an analysis phase, has sort of an architect phase with the work on the specifications, obviously then the implementation, and finally there's also a certification phase. And those 4 phases are not necessarily sort of at the same level in some sense, because the platform security architecture is written for many different audiences. The first phase is written pretty much for everyone, not just for a company building an IoT product like this surveillance camera here, but also to someone who just works on individual components, someone who wants to build, let's say, a processor that is then sold to a company who uses and develops these IoT products. This is something that you specifically notice when you look at the certification scheme, because those certifications are not meant for end consumers, but they are supposed to help developers to build, to make decisions about what processors to use and how to build a complete system, securely, obviously. And I'm going to talk a little bit more about these sort of the first 3 phases. And the certification is something that is a talk on its own. It's a complicated field. And there's a lot of information on this website, PSA Certified. So on the first phase, there is a surprising, in the meanwhile, there's a surprising amount of content available in form of best current practice guidelines and recommendations. Those were written by governmental organizations, by industry groups. Pretty much everyone contributed their wisdom to this field. So there's clearly no lack of guidance in any form. So if, for those of you who had a chance to read through some of those documents, if you are interested in IoT security, I'm sure you've seen all these press releases about hacks, and I'm not going to talk about any of those. I'm sure you're all very familiar with them. And these guidelines were written in response to some of those events and some of those news press articles and so on. And so they reference each other, which is great. They also intentionally high level. For example, I picked sort of 2 recommendations from the ENISA baseline security recommendation for IoT document, which says minimize the data collected and retained, or use proven solutions like well-known protocols and cryptographic algorithms. And clearly those make a lot of sense to everyone, but they are not directly actionable. And that's also what Paul van Oorschot and one of his students observed when they read through many of those and summarized that work in their best practices for IoT security. What does that even mean? A kind of provocative title for a paper, I would say. But they write, overwhelming majority of recommendations are not actual practices, but rather desired outcomes. And in their more than 1,000 IoT security practices that they analyzed, they concluded that about 70% of them are actually focused on early stages in the life cycle, and clearly putting a strong emphasis on the manufacturers and their responsibility for the whole ecosystem in developing those products. Because if you make a mistake very early on by omitting some of the security features, then it's very difficult to add them later, specifically once the device is in deployment and in the hands of people who are probably not educated about security. So as a developer, you are really facing a challenge because there are so many of those recommendations. In the meanwhile, there's some regulation already, although that's very, I would say, soft and very, like again, high level, mostly concerned about default passwords and using state-of-the-art security mechanisms. But how do you actually get started? Like you are tasked with developing a secure IoT product. How do you do that? And I would like to look into that question and focus and start with the Cortex A-class device, a device that you have seen on the earlier slide, and specifically focus on our trust zone technology. And there are many other security concepts as well, which we could talk about. And I reference them here if you care about the more a complete list of what those security features are. But many of them are actually known to you even from an operating system class. The whole software isolation concepts with the different, we call it exception levels or rings in Intel terminology. So that those are already powerful concepts for any software development on an A-class device. And there's Aalto University and Thomas Newman and Professor Asokan, they actually wrote a nice blog post about the history of trust zone. And I've included the link here. And I think Professor Asokan is also on the call, very insightful write-up. But the trust zone is, as a technology, is around for quite a while for A-class, and has gotten more attention over the last few years because people are more interested in developing secure products, not just like I would say also motivated by the press releases and also by the developments and the advances in the mobile phone side where some of those technologies came from originally. So if you look at what a DEE is, Trusted Execution Environment, and there's a definition, one of many, of course, in one of the IETF specification that says it's an execution environment that enforces that only authorized code can execute within the DEE. So the authorized code, I don't know if you see my pointer, would be on the right-hand side. That's the secure world that is sort of added to the previously existing system. And there's this this exception level that at the bottom that handles the transition from the so-called normal world to the secure world. And so every sort of an application that makes a call from, let's say, a regular application on a normal world, then gets passed through the layers like in a normal system call and just transitions over to get then routed, dispatched, as it is sometimes called, to the correct trusted app via an intermediate sort of operating system, a trusted operating system. And so and the data used by that code cannot be read or tampered with by code outside the DE. So the idea is that an application running on a normal world can obviously not look into the code of the of these trusted applications at any layer. So that's a pretty powerful isolation concept, and you use it on your smartphone and your tablet and hopefully on many of your IoT devices as well. Trust zone is, while it looks conceptually very simple, I would argue that it's there's obviously still potential to make mistakes because it's a system concept. It's just it kind of logically adds a new address line to make the distinction between normal world and secure world, but there's much more than that because it allows secure peripherals. And the figure, which is copied from the ARM security technology white paper that talks about this, the trust zone technology, introduces the capability to also include protection or expand protection beyond the processor. And so the different boxes in gray indicate on whether a peripheral is actually or understands the trust zone, this additional address signal or not. And if it doesn't, there needs to be some controller in front of it. that actually does the translation. There are different types of these controllers available. And the same is true for memory regions. So in a typical SoC, system on chip, you have many different components that are interconnected using some bus, whatever that bus is. And you need to make sure that, for example, a compromise in a modem, like it is shown here up on the top left side, cannot, for example, make DMA access to memory regions that are then totally bypass the security of a trust zone. And of course, those things have happened. So in the design of a security solution, like if you think of a trusted app, you need to understand how the whole system actually works and how it's secured and what is actually the security boundary of it in order to make it secure. Not necessarily a straightforward task, as you can imagine. To help developers to actually get there, they are not asked to write everything from scratch. And so we have this, or we have contributed to this project on this code. There's a dedicated website project hosted by Lenaro. It's called trustedfirmware.org, which, among other things, develops the low-level software or firmware. It's called Trusted Firmware A, A for A-class, for application processor. And I only really simplified the diagram here and indicated as a secure monitor that dispatches the call, but of course there's much more in there. Also the power management and other functions to route calls and to manage the low-level functionality. In addition to that, there's the work on Opti, which is this Secure World OS reference implementation and example applications that run on top of it. So if any one of you has participated at some of the hackathons in the IETF, previously, obviously, they took place alongside the physical IETF meeting, and now we have them virtual. And we had some dedicated hackathons like in between as well, focusing on IoT security. And so we worked on some of those projects and used hardware that supported these type of systems. And so there's a good foundation. Like this software is obviously, it's a lot of software, but it's not just reference implementation. Sounds a little bit shaky, but it's actually a rock solid implementation that is being worked on, and specifically for the researchers among you, there's a lot of development here, which I will mention in the next couple of slides. We've also advanced the architecture and the security features. So one aspect that you may have missed on the previous slide is that there was no hypervisor or EL2 state in the secure world, which was introduced with the V8.4 release of the architecture specification. And that led to a change in the software implementation to offer another layer of isolation in the secure world, which having more isolation is obviously better, as you can imagine, and may also allow to better compartmentalize the different trusted applications running in the secure world. So not only did the term trusted application change, but also to secure partition, but also the concepts changed a little bit. There are lots of details on how you would, or when you would start them, how those are maintained. And that's essentially the job of the secure partition manager, who basically manages the life cycle of these partitions. And of course, the configuration and management of memory, the message handling, and the details of how these messages bubble from the normal world to the secure world. Why are these different layers? Obviously, lots of layers. Every time you transition from one exception level or from the normal world to the secure world, you obviously need to figure out on how that works. And that's described in this so-called FFA, the Firmware Framework A specification, which is, of course, available for download. And that's where I took this picture from. So there's a lot of new development here. And of course, that code is now, or there's code being worked on to enable this sort of this state or this envisioned software isolation state, which I find quite exciting because there is relationship to the work that is being done in a confidential computing consortium where some of those isolation concepts are used as well. But I won't go into that. There's a separate, like it's a whole universe on its own. As an intermediate state, obviously for devices or processors that don't have this feature implemented yet, my colleagues obviously prepare that already, and so you can already find today code for these for the foundations of this new architecture with these services in the code base. So if you go to the trustedfirmware.org website, you can find that code there. There's also a talk given by Lenaro Connect in the Lenaro Connect conference by my colleague Julian Hall, who talks about these trusted services, because unlike previously where you basically were on your own developing your trusted services, we have now provided a range of services here, three of them listed here: crypto, storage, and attestation, to actually basically offload security functionality from your regular sort of application environment to these secure services. So what that means is, if you take, for example, embed DLS, and which can, if you enable it, use the BSA crypto API underneath, it hooks into this communication architecture, into the FFA drivers, and then passes on the call from the normal world over to the secure world, and manages, uses the services there, which is obviously a big security plus if you don't maintain the secrets, let's say, either in the operating system or even worse in the application itself. So another form of isolation that provides a lot of benefits and with software available. Oops. If we jump over to the M class, there we have also, over the last couple of years, we've seen a transition from the classical, extremely popular V7M and V6M architecture. So some of the processors that may be familiar to you are the Cortex M0 Plus, M3, M4, widely used in all these development boards that people like to use these days, over to the V8M architecture, which introduced trust zone also for low-end IoT devices. And the sort of the names of those processors is M33 and M23. And those are, in the meanwhile, also widely available in the market. So you can get them from the big silicon providers at a very decent prices as a developer board, and of course even cheaper if you build products and just buy the processor rather than the whole thing. And so how does this look like? It's obviously made very similar, or trust zone for the M class is designed similar to the A class, with sort of a caveat that the transition that was previously done through the secure monitor has been simplified to take the latency of embedded applications into account. But it was clear that now that you have sort of on the normal world, you would, in this case, it's called on the M class, the terminology changed a little bit, so that may be confusing. It's called non-secure processing environment and secure processing environment. And in the non-secure processing environment, you would run, for example, a regular real-time operating system like Zephyr. And then there had to be some code as well for these secure services, and also for the underlying sort of partition manager. And that's, as the name indicates, it's essentially the equivalent of what we have just seen for the A class. It's the trusted firmware for M class. So that the little brother, if you will, of course, tailored to the constraints that IoT devices have. So not a full-blown OS, but very lightweight. In addition to that, we've also seen companies using a dual M-class design to actually separate the security functionality out into a dedicated chip, which may be still on the same sort of system as a system on chip, but as an alternative to the previously shown V8M design. So this is something that, for example, Cypress with the PSOC64 offers, and there the difference is then, instead of doing the transition from the non-secure processing environment to the secure processing environment, sort of locally on the CPU, you actually perform an inter-processor communication call. So that's obviously a difference, and we'll go into a little bit more details on how that looks like. But what if you could actually extend this whole concept? And that's what was done with a technology, or with under the code name of Corestone. And this is a system on chip, sort of a reference design that developers can use to have essentially a blueprint for an SoC that contains an A-class combined with an M-class subsystem, as well as a secure enclave. And you can see that on this diagram over here. So this is an example. So there are different reference designs. This is the Corestone 700. And these M-class processors, for example, are used in case you need some real-time, classical real-time performance, motor control, whatever, where you need to have a very tight latency bound. The A-class obviously delivers the performance, and the secure enclave is meant to control the whole system. That's why there are firewalls all over the place. And we look in a little bit more into the software of such a system, because not only do you not need to worry about the verification of that system, of this SoC design, but you also get the tools alongside, because you want to do, during the development phase, you want to maybe run your design on an FPGA. You may even want to emulate this on a fixed virtual platform. It's kind of a QEMU system to actually run this like purely on the laptop and see how this works. You want to have the whole built environment. In this case, it uses Yocto, the Yocto built environment in combination with CMake to build the whole software stack for the A-class and M-class. And so I will show you there's obviously a lot of software. And this is sort of an example of what that software stack looks like. The left-hand side is sort of the server-side infrastructure, a kind of a device management solution. And on the right-hand side, you have the host processor on the top with the Linux and trust zone we talked about previously, with some applications like device management, some object detection, or whatever you want to run it. And then on the bottom part, you have the secure enclave software, which again uses the trusted firmware M with the secure partition manager, with the secure services. And as I mentioned, there's the communication between the host and the secure enclave needs to happen somehow. And again, standards come into the picture here, because it turns out something that I wasn't aware of, that there's work, obviously, by other companies to standardize this interaction, and to also provide, so even standardize the queue management or the buffer management. So there's an OASIS standard word IO, and there's OpenAMP, which contains of word IO, and Api message, which I compare to UDP, kind of UDP over a message handling unit, a shared memory interface to actually communicate between the host processor and the secure enclave. So this is quite a kind of interesting approach to actually make this standardized and simplify it for developers, so they can easily talk from the Linux side over to the secure enclave and execute the services over there and obviously get the response back. What you also have there, or what you also want to have as a, if you follow the guidelines, is you want to have some root of trust here, hardware side. So like some crypto IP to manage the whole life cycle, to deal with secure debug and so on. There's also typically a ROM, or there is a ROM-based bootloader, immutable bootloader, followed by one or more stages of bootloaders that are involved here. So like here's a flow. If we take an attestation service, attestation information or the request for attestation comes via device management software, bubbles through the Linux stack, goes over the MHU, uses OpenAMP and API message to travel into the secure enclave. There's the attestation service, and that needs to access obviously the root of trust. And typically you would use measured boot to get information about what happened during the boot process, for example, fingerprints about the firmware image that was booted, which is then passed back along the same way to the verification service. And I'm going to talk about the standards that are being used here in a minute. So it's a lot of software. And I look at the time, glance through. So there's it may be surprising on how much how large a stack actually is to get something like this working. But here is a little bit more detail based on a crypto example, which is probably something that resonates with most of you. If you take an application, whether that's a benchmarking application like SecureMark TLS or the classical device management software, when it makes this call of the previously mentioned BSA crypto API, normally the library would be linked to the application. But in this case, the library, of course, still has been linked with the application, but it knows that the implementation of the crypto functions are actually not on the host processor based on configuration. It knows that it has to do essentially serialize the API call, which is the API call is a regular C API. So that has to essentially be conveyed over to the secure enclave via OpenAMP using the shared memory. To do that, there's a separate API, the so-called BSA client API, to actually establish a session with that service, because the host needs to find out like what service do I need to talk to, and then establish that communication with shared memory involved most likely. And then the call is actually made, deserialized, and then passed into the crypto service. And depending on what function is being called, this may then directly translate to a call to the hardware crypto, or if that crypto functionality is actually only available in software, it's actually handled here. And that code is, of course, also available. That's part of MPAD DLS, and the whole sort of stack, if you will, is that's what you find in as part of Corestone, which is also available as software. So this, in a nutshell, there's a lot of software involved. Software that is available, for example, the DFM project, which I wanted to talk a little bit more about because it's, I think, really essential for developers writing code on a Cortex-M class device if they want to like develop the watch, the smartwatch we've seen. That would be a good target use case, because you more or less get with a minimal effort to a very good starting point. Of course, you still have to, as a developer, you still have to make up your mind, like, what are the threats I'm going to protect against? What is my business model? What out of all the threats, which ones do I want to cover, and how? You still have to go through that process. So nobody can do that job for you, at least not generically. Of course, you can hire someone to do that job, but that's still something you have to do on your own. but creating the building blocks and the foundation to decide what you want to incorporate and how you get to a good starting point is something that we have hopefully provided with Trusted Firmware M. So I mentioned previously already, non-secure processing environment may run a regular RTOS like Zephyr, Riot, or whatever your favorite RTOS is. There are many of them. And the core of this is actually handling the routing of the calls, and also establishing the partitions. As the name sort of indicates, it's the partition manager. It creates the partitions when it started, and deals with the communication, sort of mediates the communication to the sort of non-secure processing environment, but also to the lower layers. So to the hardware, it also obviously does crash handling and so on. And also included in the project, in this software project, is a bootloader, which is also based on an existing bootloader called MCU boot. And I'm going to talk about this in a few minutes. So that the secure partition manager can actually do its job. And I think from a computer science point of view, that's quite interesting, because so many things in operating system design are really about software isolation. And so the way it does it is the partitions in which services run, one or multiple, are described in a manifest format, which is a JSON-based file that lists, besides classical metadata like the identifier, the endpoints and the services it exposes and the functions those services have, but it also lists resource requirements like how much stack and heap it needs, what access does it require in terms of IO regions and interrupts, and also access requirements when these services talk to other services. So this can be defined upfront, and then the tools take care of the rest to actually build the images, which is a non-trivial task because there are configuration options to allow different levels of isolation to be provided based on hardware security features that are available on Cortex-M processors. So for example, if you can isolate each partition from each other, or to have only isolation between the non-secure processing environment and the secure processing environment. So it depends a little bit on what you want to do. The services inside and the partitions run in a single threaded environment. And of course, all the state is private to them, and which also has implications for the software design, as one can easily see. There's obviously a lot to say about those things, which I'll have to point you to the specifications on the APIs. So far, we've published the crypto API specification, the attestation specification, secure storage firmware update, and also the APIs that the partition manager uses, as well as the API that allows the communication between the non-secure processing environment and the secure processing environment. Also of interest, I believe, to this group, to this audience, is authenticated debug access control, which will be added in the future as a service, which I think is quite important if you think about not only sort of debug during the phase of like prototyping, but also in a later stage. And there's also, since this is an open governance project, there's like the mailing list, there are conference calls, there are like obviously the repositories, but there's also roadmaps for what people want to add in the future. So it may be also worthwhile to have a look at that. I will talk about two of those APIs or two of those technologies in a little bit more detail because they relate to standards efforts in specifically the IETF as examples. Attestation is one of them, and this is work done in the IETF RATS working group, a funny name for a group, but the the group is working on architecture specification, protocol specification, but also, I think, most importantly, a specification for a token, an entity attestation token. And the idea of this token is that the attester, in this case, that would be our IoT device, when asked, and this is sort of the request coming in with the nonce, it provides information to a relying party with information in form of those claims, of course, protected, to demonstrate to that relying party that it has been manufactured by a specific entity. It provides a specific security posture. It has a specific software running on a device, and so on. And maybe have watermarking information, who knows what. There are a number of different claims defined, and of course, room for extending those. And that will allow a relying party to actually make an assessment whether that device is like running in a simulator, or whether this is a real device, whether this is a device of a manufacturer known to the relying party, and so on. And that, of course, requires some backend infrastructure to actually work in practice. And it requires manufacturers to provide keys to the device, so otherwise the token cannot be signed. And it also requires the role of a verifier, because some of the data that gets passed with this e-token may not be immediately verifiable by a relying party, because that party may not know what the expected value is, what is supposed to run on that IoT device. Like, is it fine if that bootloader has this and that fingerprint? And that's the role of the verifier to provide. And as I mentioned, IETF specifications are used here in various levels. At the top level with the entity attestation token, there's the reuse of the CBOR web token, which is a token format that was developed in another working group, and uses like the well-known signature algorithms that we all would expect. And the claims are standardized in a CBOR-based format, and there are a number of them, and profiles actually can trim them down. So we've developed one profile to trim down the specifications that are used with our M-class devices, and also sort of makes decisions about what signature algorithms to use, because on these resource-constrained devices, you can't just implement all these algorithms. In our case, elliptic curve cryptography is popular on our devices, but I know that other people are using RSA for other environments. And there are numerous specifications, and to look this up, to dig into the details of this, worthwhile to point out, I think, is that we have developed software components to build this verification service that I mentioned on the architecture slide. It's a project called Verification of Attestation, VERASON. It's a little bit constructed acronym, but there's code available to set up such a service and to run it if someone wants to use that, or use that as a building block. And there's also, I think, a well-written white paper available that explains sort of the bigger picture of how we use these standards. Secure boot and firmware updates is the other topic I want to mention, because again, there's an IETF effort, and for many, this is it's almost something that gets forgotten, because it looks on one hand very simple, because all a bootloader does, it needs to figure out like what code do I start in terms of the application firmware image when the device is powered on, which by itself doesn't look like a tremendously complicated task. But once you add all the security to it, it gets very tricky, because of course, there's the question about which crypto, asymmetric, symmetric. There's the question about like how many images do I need? Where does the image need to be? How many images do I want on the device? Is it encrypted? How does the key management for encryption work? Does it require decompression? Is it a binary diff? Am I doing a differential update? And so on and so on. And then there are peripherals that need to be initialized because you may need to copy things around before you can even boot them. So and if you look at the MCU boot, you will see that this is more than a few lines of code to actually get all of this done. Specifically when the security functionality is there. So what you typically find on those, and this is MCU boot is for M-class devices, and normally the flash layout looks like this. So you have one or more bootloaders on the flash and the flash often on devices places some constraints on alignment. So that may be something to think about up front, because if you don't take the alignment into account, you will corrupt code of adjacent slots, for example, because you erase an entire slot when you write something. So in this case, since these devices don't use position-independent code, you actually need to place the code in a specific place. You can't just take a firmware image and move it, let's say, to this slot, which is a different address in Flash, and then execute it from there. So most, actually, probably this is widely known, but on IoT device, low-end IoT device, you execute the code straight out of Flash. You don't copy it in the normal circumstances to RAM to execute it like you would do it on a desktop PC. So you execute it from there. And so if it's not position independent, if the addresses need to be, they cannot be just moved around, or the code cannot be moved to a different address. So you have to, the bootloader has to swap the image before it can start a new one. So in this case, this slot is used for the new images. The old image is copied over to this slot, and vice versa, using a scratch region. So when something fails, you can fall back to the old version. Otherwise, your device is bricked. Something that I'm sure if you have used older computing devices, you may worry about firmware updates, because if something goes wrong, then nothing works anymore. These are mechanisms to ensure that that the devices are still functioning. And there's also the work split that needs to be taken care of or thought about between the bootloader and what the firmware update service, which runs, which actually gets the new firmware image in the first place, what that needs to do, because the bootloader rarely implements the networking stack, because that would be complicated. So the bootloader would then be huge, and you definitely don't want that. So that's the sort of the work split between the MCU boot as a classical secure bootloader and the firmware update service, as well as the device management service, which I will mention in a second. And actually, I need to speed up a little bit. So this is the pointer to the project. Definitely worthwhile to have a look at it, because it is used in other operating systems as a bootloader. So real-time operating systems for IoT devices, not just by DFM, but also by Zephyr and EmbeddOS, and I've seen also links to RiotOS. And it's something that we found useful and joined that effort, and very, very happy with this. I will just glance over this. So there's IDF work on defining a standard for a manifest specification. And so the manifest is the metadata for the firmware, which includes the wrapper, because when you get the firmware image, you want to make sure that it hasn't been tampered with. Nobody swapped code out or modified it or did something else to it, because that can lead to endless problems. And it again uses CBOR and COSI. What is new in this format, what is maybe a little bit unusual, it's a behavioral manifest. It essentially contains scripts on the script that you execute to do the firmware update, which is, I think, novel. And there's obviously like the supplementary specifications defining the whole architecture of the firmware update. And of course, code available for this as well. So this can be tried out. this is close, I would say close to completion, but not completed yet. Like the rats at the station work, it's also close to completion, but even though we have implemented it already, but the ATF process needs to sort of pass through to make this final. One short slide about the manifest structure. So it contains a long list of features. If you look at the documents, it describes many different use cases to actually demonstrate that if you, and that's the nice thing about doing work in a standards organization, you get exposed to all sorts of different use cases, not just the ones that you have in mind. And so you cover much broader scenarios in the end. And I think it has a lot of potential as a technology. The final thing I want to talk about, and something I think gets, because it's probably not such a hot topic at the moment, but I think it's essential for an IoT device, because you not only need to think about like, what do I do to get it basically out in the field and get it running, but also how do you maintain it over its entire life cycle? And that's what device management is about. And I'm a big fan of the lightweight M2M work done in the OMA, because it has evolved over time to become a, I would say, almost transport independent because of all the number of transport it supports in the meanwhile, and also the flexibility it offers to manage different sensors, actuators, to make configuration on the device, to do firmware updates, like, because you need to get the firmware image with the manifest to the device in the first place. And to have that whole sort of maintenance, like diagnosis, and all these capabilities over really a wide range of also radio technologies. So here's how that sort of works from a interface point of view. There are different so-called interfaces, which are just the communication interactions between the IoT device, which runs the lightweight M2M client, and the server-side infrastructure. The first one is like really provisioning credentials, which is obviously important if you want not just provisioning the initial credentials, but also then rotating credentials if they expire, to deal with access control lists, to provision configuration information. And then the last three are more about the regular application usage in many cases, because you need to have the device connect to the server infrastructure to provide data when asked, or to report about changes in an asynchronous fashion. That's what the information reporting interface is about. So if you haven't been exposed to lightweight M2M yet, I have a couple of references in there, and I definitely think it's a great protocol. We've done a lot of test fests. We have many implementations and also many open source implementations as well. So this is the stack it uses, and you see like the messaging on the top, lightweight M2M messaging based on these interfaces from the previous slide. But then it reuses a bunch of technologies all the way from CoAP to MQTT, HTTP, and so on. All these different security technologies are being used, and they have been tested, and there's obviously some room for tailoring to specific deployment use cases. So obviously someone who uses, let's say, LoRaWAN may want to opt for a CoAP-based communication infrastructure. Whereas, for example, if you have a regular HTTP environment or MQTT, you want to go for like the classical TLS, TCP type of stack, for example. As promised, the links version 1.2 of the specification was released end of last year. So it's pretty fresh. We just had a test fest. Implementations are doing great, and there are a few very popular ones offering even sandboxes, so you can play around on these sandboxes without actually having to install anything. And there's a gigantic object registries extending sort of the description of the objects that you can control and get information from on an IoT device. I think this is also very important to make those the device management practical. If you already have data from sensors and so on that you know how to access in a convenient way with really minimal bandwidth overhead. The last thing I want to talk about is that's a new work that relates to the device management is what is known as late binding. And if you look at the top part, it describes roughly on how the supply chain works today with devices that are being built for a specific purpose. Often, of course, IoT devices are built such that they are used, not just, you don't typically sell the hardware in a store and then you get it to the end customer and then the customer figures out on how they want to manage their devices and so on. But instead they are purpose built. They're also very constrained, so there are limitations in that sense. So if you have many of the industrial use cases, you just have a purpose built, let's say, precision farming solution. Of course, you can tailor it to different customers, but they are really purpose built. And that's what the topmost figure is supposed to indicate. So you have, let's say, a precision farming solution for one customer who uses, let's say, Amazon's device management solution. And the device is configured and provisioned with a firmware that works with Amazon's AWS. And the next device is maybe a different precision farming equipment, but it's probably built differently, but it runs with, let's say, Microsoft's Azure for IoT. And then there's yet another one and so on. And so, so all the information that is needed to operate the device is actually provided into the factory so that the device is manufactured according to those specifications. The late binding allows or envisions a model where you would sell devices and they all kind of the same at the beginning. So they are maybe all devices that offer precision farming capabilities, but then when they reach the customer decides, hey, I want to use the device with, let's say, Amazon or with Pelion device management, and then they do this so-called late binding, a kind of provisioning or onboarding step at the time when the device is unboxed. And that's what has been done as a specification work in the FIDO Alliance with the FIDO device on board. And this is the figure, sort of the architecture figure, that 10,000 foot sort of picture. And what it essentially does is it, instead of provisioning or binding it specifically to a device management solution right at the factory, you would delegate this and you would provide the code of the FIDO device on board and into the device at the beginning in the factory. And then the device, when it's powered on, it would talk to a rendezvous server. And that rendezvous server, operated by someone, not decided yet who would do that, would then learn via so-called vouchers about the current owner that this device has. And the current owner can then sort of re-provision it to use it, to use that device and to control that device. Obviously quite a security sensitive task. And so with this benefit of doing this late onboarding, of course, there's the price to pay that you have to secure this, this voucher, ownership voucher transfers through the supply chain. So every time the ownership changes, this voucher needs to be extended and re-signed, and then needs to be presented to this to the new owner, and the new owner then needs to inform the rendezvous server about this change. So this is very new stuff, sort of like straight from the press. Was published, I think, either March or February. And so the specification can be downloaded here. So I only gave you a sort of a sneak preview of how it looks like. There's also source code available. It's currently not up to date to the specification, but it refers to a prior solution that was donated by Intel called Intel Secure Device Onboarding or Onboard, and you can check it out there. And with this, I would like to, and I think it's time to jump to some conclusions. And I think, or I hope I have shown you that although these IoT devices are kind of tiny, and in like, if you look at the processors and look at the development boards, you wonder like, what can be so complicated with those? But developers who have to work on some products, although they are given all these recommendations, it's still a complicated task because they need to understand so many things. And our contribution to this is to actually produce code and of course documentation alongside the code and APIs to make it easier for those developers to actually get to a working system. And of course, with collaboration with others, we get faster from the specifications, like the EAT specification, like the SUIT specification, like the lightweight M2M specification, to then have code that many developers can use, so that they can actually then use that code tailored to their needs, to their threat model, to their business model, to get to deployment that is hopefully then also secure if they make the right decisions. And in general, I think we can get to more secure IoT devices if we use standards, use the standards we have, and also contribute more to the standards work. So I would encourage everyone to participate because, as I mentioned in the introduction, there's so many more people who are interested in breaking things than designing security technology that I think we are understaffed in the standards organization world. I also think software reuse, or in like contributing to software and collaborating in the software area is really important. And that's why we have joined those projects that I mentioned to work with others, to work with our partners, to work with universities there and consultants and researchers to improve those specifications. And there's a lot of development going on. I think also for researchers that could be pretty interesting. There's interesting stuff there. And then in the end, because also hardware is complicated and the hardware software ecosystem is tricky. So we also contribute some hardware reference design like the Corestone to get people or companies faster from the idea of an IoT product to actually to the real product. So with that, I hope you guys are encouraged to contribute code to help us and to help the whole ecosystem to improve IoT security. And with that, I'm happy to take questions.
Thank you, Hannes. I just realized that there's no chat option available, so I don't think people can ask questions over the chat. I think in my overzealousness to prevent some things, but I see that Valtteri has his hand raised. So Valtteri, go ahead, unmute yourself and yeah, ask.
Yeah, thanks a lot, Hannes, for a great talk. So it had really lots of information. So I just one detail of the IETF work. So this seems that the IETF work on this sort of platform security area. Is it concentrated on the IoT, or is there some work or some reason why there isn't any work on other devices or other platforms or like cloud?
That's a good question. Hi, Valtteri. Haven't seen you for a while. Yeah, that's a good question. So I think like the IETF is, like many other standards organizations, are really contribution driven. So I think probably the reason why that there's so much work on so much standards effort on IoT development rather than, let's say, cloud or some other topics is really based on the people who participate. There's also the IETF prefers to work on solutions that are more communication security oriented, and so some of the IoT security work was lacking standards, so communication standards. So like, for example, let's say communication security work definitely has seen an increase in the IETF with the IoT work. But in other areas, you could argue, like the attestation, that this can and most likely will also be used in sort of areas which have little to do with IoT. So I definitely see it being used in the future in, let's say, in routers. I think also on the server side. So we haven't seen too much successful attestation work in the past, and I hope that's going to change. And I think with the work on, let's say, confidential computing, that will heavily rely on attestation. We will see more of those. So I think it's I think we need more people from sort of cloud environment, and also maybe an attitude change towards away from the classical communication interfaces would also help. So I remember there was a lot of reluctance to even think about standardizing mechanisms that relate to the host security itself in the IETF. You could argue, for example, many of the APIs that I mentioned, they would probably not be accepted for standardization in the IETF, even though, in my opinion, the boundary of where an API ends, like a classical C API, and where an interoperability need arises is fuzzy. Like, as I had shown, like as you transition over to another processor away from like calling into one library on the same machine, you suddenly have an interoperability need. So I think there is potential there for other areas. It just needs the people to contribute to that. I hope that makes sense.
Yeah, thanks.
So you already have a very good example with Valtteri taking the lead in unmuting and sharing his video and asking questions. I would encourage, if anyone else has questions, to do the same. I see Jilang has a question. Go ahead, Jilang. You can unmute yourself and ask your question.
Okay, hello, my name is Gilang. I'm a SECLO alumni. So I actually have been wondering that we actually learned about the TEE and stuff from the courses when we were in SECLO. However, I have been wondering, is there any way, like for a regular programmer, that if they want to make a secure application inside the secure OS itself without actually having to make a secure firmware by itself? So therefore, like if a developer wants to make a secure service, like their own secure service, and run it inside the secure world, is there any like a mechanism to do that? Because, like, for instance, that we know that some recent technology, like by Intel, they have an SGX that you can program, you can make a program and run the code inside the secure enclave and something like that. Is there any something that we can achieve that in the ARM platform? Thanks.
Thanks, Gilang. Yeah, so it really depends on the platform you're using, because I suspect that the area where you wanted to use it was probably a mobile phone or a tablet, right? And there, of course, the company manufacturing the device, they make decisions about what they allow and what they don't want to allow. And so if they don't want anyone else to push code to the secure word, then they can obviously do so. And that's just not their envisioned use case. However, we are seeing, in light of these confidential computing, we see more and more of those use cases where you want to, very much like SGX or related AMD technology, where you want to allow developers, ordinary developers, to just push code to an enclave running on a cloud environment. And I think we are just at the start of this, and there are several different sort of environments or platforms being developed. And if you go to, if you search for Confidential Computing Foundation, I think it's called, a consortium developing different sort of solutions to actually run software there in such enclaves. There are obviously different design choices on how easy or difficult you want to make it for developers to actually run software there. I think that's that will be appealing to many. In an IoT context, it's obviously the trusted applications, they would be used purely for security functionality, and you cannot expect as a, let's say, as a user, that you would just go ahead and just update code on your IoT device yourself and run it in the secure world. But I think for ordinary test purposes and or for even development purposes, you could use the confidential computing environment to do that. And you can also just get a development device like a SD microelectronics MP1 device and just run the stuff on your own. You could also use, for example, the Microsoft Open Enclave SDK to run the stuff in Visual Studio in simulation. It would even spawn up QEMU instances to just sort of emulate things. So you actually have a lot of choices depending on what you want to accomplish. Does that make sense?
Go ahead, Jilang.
Yeah, okay, yeah, thank you very much.
I will look up the link to this confidential computing organization because they're going to have an event coming up fairly soon. I will do that. Maybe, I don't know if you, Mohit, if you distribute anything. Let me look.
Sure, we can share the information later. Are there more questions from the audience? I have some questions, but I want to let the audience have the first choice. So yeah, Valtteri, go ahead.
Yeah, now before Mohit gets the floor, I would like to ask about this standards landscape in general in the area of, let's say, near ARM, or let's say in platform security in general. So because there are quite many of these consortia and standards organizations, are there too many, or are they somehow overlapping, some of them, or competing?
Yeah, there are definitely overlapping and competing efforts, and of course there's a lot of on one hand, you could call it the not invented here problem. On the other hand, you could call it innovation if people in the end really come up with something truly different. And for some of those efforts, the jury is still out there. But it's often very hard to tell upfront whether a specific technology will be successful. Like, you can go from the bottom to the top. If you look at how many different radio technologies there are for IoT communication, from Bluetooth Low Energy with mesh to 15.4, Zigbee, blah, 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 cellular, LoRaWAN, and so on. You could argue that maybe that's too many. On the other hand, many of them try to address a different niche. And there is overlap, but it's hard to say like which one will win. Because there's more than just the technology that like the technology, like really the specifications and that play a role here, but it's the whole ecosystem that matters. And the same is true for if you go up the stack, there's still lots of proprietary developments, which I actually have a hard time understanding why people do that. I think that proprietary developments are more problematic than the too many standards, because the standards to me have several advantages. Not only is the interoperability something that gets improved, but it's also the quality of the specification that really makes a difference. And specifically, if I look at IETF documents and how much time is spent on improving and analyzing the text and the protocols that are being developed, it's just amazing. It's something that individual companies would never be able to do themselves. So that's why, and also researchers are more incentivized to look at and analyze the DLS specification than the great idea of some random company who has gotten the idea to come up with a new security protocol. So in that sense, yeah, that I sometimes wish some efforts would be a little bit more coordinated and organized, but I think that's the world we are in. It's the same. It's the same everywhere. I think it's also true for non-standards activities that there is often a lack of coordination.
Thanks.
And actually, in the meanwhile, I have let me share my screen to the previous question. So this is the effort that you may want to look at. This is the Confidential Computing Consortium, and it has a couple of projects. And these projects, like I mentioned, the Open Enclave SDK that allows developers to build trusted these DE applications. There's work that my colleagues do on Veracruz on privacy preserving distributed systems, and so on and so on. There are more projects out there, and depending on obviously each project on a high level, they all try to do the same, but the details on where they put the boundary of what goes into the DE and what the developer has to do differs substantially between those. And I think we will see a lot of activity in this environment just because of the technology that has, on the hardware side, that has become available. So it's definitely a great place to be in at the moment for computer scientists, because there's just new stuff coming along that people haven't really utilized yet in their products, in their new work. So this is they actually have a good white paper comparing confidential computing against some alternative technologies like homomorphic encryption, which also tries to protect sort of the computing that happens on. So you essentially with this, the idea is that you make computation on someone else's hardware that you do not trust, and you still want it to be secure. So that, I think this opens up tremendous possibilities. So have a look at that. It's probably something you want to get involved.
All right. So is there any more questions from the audience? Otherwise, we have 3 minutes, and I'll ask my own questions. I don't see anyone raising their hand, so I'll take this opportunity to ask. So Hannes, I have 2 questions, and I'll ask them because we are running out of time. So I'll ask them together, and you can see how to do them. So one question is about this FIDO device onboarding work. Is it more focused on enterprise use cases or home use cases? I'm wondering, like, if there is, like, especially in terms of privacy implications, if ownership information or ownership transfer information is somehow like visible to everyone. Is that an issue? And I guess there will be more ownership transfers, let's say, for home personal use cases and enterprise use cases. even the mergers and acquisitions happen, I think there the environment is a little bit more stable than home, where I buy and maybe after a year's use sell them on Facebook or something. The second question is related also to what Jilang was asking. I don't know if you share this feeling that there is somehow a gap in like how many people these days write C code and then write secure C code, and now also need to learn about virtualization and trusted execution environments, and know how to understand these hardware reference diagrams. I think the number of people who like check all the boxes is like smaller and smaller. So isn't that becoming also an issue of like, how do we get people who now not only know how to write C code, but write secure C code, also understand how to utilize trusted execution environment?
Yeah, you bring up an excellent point. Like clearly, it's difficult for students, and not just for students, for embedded developers as well. When I attended developer conferences, like let's say 5 years ago, like it was like if I suggested to someone to use an off-the-shelf bootloader, to use an RTOS, they were sort of like looking at me and saying like, who's that guy? You know, like that's he's not serious. Like you write everything from scratch, right? And as we started to add all the security stuff and internet connectivity and so on, the transition from embedded to IoT is just day and night. And that's something difficult to swallow. And along comes, as you said, like you need to understand the hardware, you need to understand the software, you need to understand the development environment, and that's really something that you learn. So apparently, Aalto University is much better at that because people are already familiar with Corestone, but you rarely see anyone who understands like those hardware details and the software development. Even if you had maybe learned C at the university or at work, it's still a long shot from writing C code that is remotely secure, that you can actually use it in production, or any code to use it in production. And then understanding the build environment like Yocto, CMake, and all these different tools. Like this is a lot of work. So yeah, it's difficult, and I think that's where the need for collaboration and having pre-built stuff actually is really so essential, because otherwise, if you try to do this yourself, you will not get anywhere. Like the stuff that I was talking about, like even for, some small parts of it, our device management client with the supplementary software has around 100,000 lines of code. Of course, you're not compiling in all of this. If you take out the trusted firmware M code, that has about 200,000 lines of code. Like ARM and N, I mentioned an application, the object detection application, like that has 1 million lines of code. So like, it's like, you cannot do that yourself. It's impossible. So you have to rely on many others to get this stuff out there, to do sort of the to do some of the work with you or for you. That's the problem. Final response to FIDO. I think FIDO, it's an interesting idea. There will be a lot more research that needs to be done to see whether whether the business model is a good one with this late binding. So I brought this up because there are some researchers here who may want to analyze things. There are obviously some security challenges which are pretty obvious. And as you said, like, how do we practically do this? Like, how do we, if I resell something, do I need to now sign something? You need some tools to actually sell it. It sounds difficult to me. Like, and how can I be sure that it actually works, that my devices are not taken over, that I don't take, can someone be sure that I don't take over the device again, and so on and so on, So I think that's the nice thing. There's always some new activity, and for researchers to also explore whether this is really rock solid. And I think that's where you guys come in with all the research work you guys do.